or if we came into contact with acids and bases. For instance, vinegar, which is acetic acid, also known as ethanoic acid, is edible. It's in lots of good foods. Sulfuric acid, on the other hand, is toxic in the same concentration as vinegar. It's poison to our bodies. It starts doing dangerous things. So the strength of an acid or base measures how completely that acid or base ionizes in dilute aqueous solutions. So ionizes is breaking into its parts. How fully does it break into its ions when it's put in water? The more it ionizes, the stronger that acid or base is. So let's refresh ourselves a little bit. If we're dealing with a strong acid, for instance, sulfuric acid, and we think back to Bronsted-Lowry, they said, well, H2SO4, from hydrogen being a 1 plus and sulfate being an SO4 2 negative, they crisscross, I get H2SO4. Well, I'm going to put that into water, H2O. It will dissociate almost completely into H3O 1 positive plus HSO4 1 negative. It's because this is acting as an acid. It's donating a proton to the water, so that's a base. This to get in the reverse reaction, which is going to be much shorter length of an arrow because the reverse reaction is not happening at much, so their forward reaction is almost completely putting it into its ions. If it were to go back, the H3O now would be the acid, the conjugate acid, and the HSO4 the conjugate base. So just a little refresher on that. If we deal with a weak acid or a weak base, the arrows that we're going to use are going to be much more equal because they don't dissociate completely. So the equilibrium is reached, and either the reverse reaction is favored or the forward reaction and the reverse reaction are nearly equal. So how can we tell? We can tell both experimentally and theoretically whether something would be a strong acid or a weak acid. So theoretically, we could look at a compound and say, well, this hydrogen is bonded to an electronegative element, and I can use that to determine whether it would be acidic or basic. So if I have hydroiodic acid, HI, I know that iodine is low in the halogen group compared to bromine and chlorine, which means it's going to hold that hydrogen less tightly, so it's going to dissociate more. So since it dissociates more, it is a stronger acid than bromine, which is stronger than chlorine because it's also below chlorine on the periodic table. We don't consider hydrogen fluoride in this because it's not going to dissociate as well in water because the strong hydrogen bonds between different molecules of hydrogen fluoride is going to hold them together quite tightly. If hydrogen is not bonded to an element but it's bonded to a polyatomic ion that contains oxygen, I can use a similar way of looking at it. So the more oxygens that there are compared to the hydrogen, so we're dealing with ratios here, the bigger the difference in the ratio, the stronger the acid we have. And again, that's going to deal with electronegativity values in the long run. So HNO3 is a stronger acid than HNO2 because it's a 3-to-1 ratio as opposed to a 2-to-1 ratio. The bigger the difference in the numbers, the more acidic it is. Almost all organic acids are going to be weak. That's our vinegar, our acetic or ethanoic acid. All three of those things are the same. They're going to dissociate very little when put in water. So looking at this question, which of the following is likely the strongest of the acid? This one has a 3-to-1 ratio, so that is our strongest acid. This one doesn't even have a hydrogen, so that doesn't count. We have 4-to-3, 2-to-1 in the last one, so C is the correct answer. Continuing on with acids, experimentally, we can tell if we don't know, let's say we have two unknown beakers that only the teacher knows, and you're asked to identify which of the two solutions is a stronger acid, and you're told that yes, the concentrations are the same, so you're only looking at how much it dissociates. You could do it in a couple of ways. First one, we can look at the dissociation and have a conductivity tester, which we've used before, to identify whether there's a lot of conductivity, so a lot of dissociation, so strong acid, as opposed to a semiconductor, which has a lower amount of dissociation and therefore would be a weak acid. With equal concentrations, the pH of a weak acid is going to be greater than the pH of a strong acid. So that means closer to 7, further away from 7. And a strong acid is going to have a higher reaction rate or a faster reaction rate than a weak acid with that same thing. For instance, looking back at our notes from the last day, if we took a metal, let's say aluminum, and react it with a strong acid, it's going to react very quickly to produce a lot of hydrogen gas, so a lot of bubbles quickly. If we took it, let's say vinegar and aluminum, the same amount, the same concentrations, everything the same except just a different acid, its reaction rate is going to be much slower. The bubbles will not bubble as quickly. There is a demo on YouTube, if you look it up, conductivity tester, under Jen the Chem Lady, to see a video of the demo that we do in class. Some common strong acids to memorize: HNO3 nitric acid, HCl hydrochloric acid, H2SO4 sulfuric acid, HClO4 is perchloric acid, HBr is hydrobromic acid, and HI is hydroiodic acid. Bases, experimentally, they're determined practically the same way as acids. If we have a greater amount of dissociation, we have a greater conductivity. So with equal concentrations of bases, a weak base is going to have a pH less than that of a strong base. So again, we think of our pH scale going from 0 to 14. 7 is neutral. It's closer to 7 if it's weak. The higher up it gets, so between 8 and 14, the closer I get to 14, the stronger the base is. And just like we saw with acids, a strong base is going to have a faster reaction rate than a weak base. So some common strong bases to memorize are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide.